So thank you very much. Thanks, Florian, for organizing this, even though it's finals week, I understand. And thank you, Manjul, for having me here for a few months. So I want to talk about this problem of reducing Galois representations mod p and what the local shape of these representations are. So these are modular representations, GL2, very classical sort of problem. Let me write the title down. Okay, so we're going to start with the cusp form. Let's assume it's a new form, eigenform, etc. So I'll call that primitive. Any weight bigger than 2, any level. And for simplicity, you can see I've assumed that the character is trivial, but it doesn't really change the problem. Everything gets twisted by square roots of epsilon or something like that. So this is no less general, just less technical. Let's fix a prime, which is away from the level. So this whole talk will be about sort of the good reduction case. And for simplicity, even though one can do p equals 3 in many cases, let me just assume p is bigger than 5. Okay, and so then we have this mod p Galois representation. Attached to f and the prime p. And so I want to study this representation on the decomposition group at P, so the PP representation. So to do that, one needs these characters, which is standard. So omega 1 and omega 2, let them be the fundamental characters of levels 1 and 2. I'll just call the fundamental character of level 1 omega, just the mod p cyclotron character. Orders are p minus 1 and p square minus 1. And it's known that this mod p representation on decomposition at p, it's either reducible or irreducible. That's not saying much, but there's also some sort of these fundamental characters of level 1 or level 2 appear. Let me take the semi-simplification. So where a and b are integers, maybe c. Lambda is an fp bar on 0 element, mod p element. And this mu lambda is just this unramified character. So I'm going to normalize it so that geometric Frobenius goes to lambda rather than arithmetic Frobenius. This is an unramified character. On inertia, it's trivial. So it's known that the representation, at least up to semi-simplification, looks like this. And one can ask which case occurs and for what values of a, b, c, lambda. Yeah, so it's a pretty basic problem. Notice as you vary through, if you fix the prime p and vary through all modular forms of all weights and all levels, capital N prime to p, infinitely many modular forms and Galois representations, but this is more or less a finite thing, right? These characters have order p minus 1, so there are finitely many exponents here, finitely many exponents here. So this is sort of infinitely many things falling into finitely many buckets, and you want to understand which bucket you fall into. Okay, so there's this key's definition, well-known definition. So the problem seems to be controlled by the slope of the form. So let V of be a p. So this is just some positive rational number, p-adic valuation of AP. So let this be the slope of f. And it's well known that if the form is ordinary, and so that's the generic case, then this thing is always reducible. So this so-called ordinary case. So AP is a unit, so you can take its mod p reduction. It's a non-zero number. So there's just the unramified character, which takes geometric Frobenius to AP. And it's reducible. So the star there, that star has something to do with companion forms, but I don't want to get into that in this talk. So we're only going to worry about things up to semi-simplification. Okay, so in some sense, this problem is 99.99% known because most, sort of primes are ordinary for forms. So, but it does happen sometimes that P divides AP, or the p-adic valuation of AP is positive. In this case, not very much is known. It's sort of surprising. So let me tell you what's known, and then let me tell you what we can do. So in this case, the characteristic zero representation, rho f, so not this one, but the one into GL2 of a p-adic field, is fairly rigid. Let me just write it as VKAP to emphasize that it only depends on the weight k and this number AP. So, so for the experts, this is some crystalline irreducible representation of GQP. Hodge state weight 0k minus 1, characteristic polynomial of crystalline Frobenius is the usual thing, x squared minus AP, x plus pk minus 1. Determinant is k power k minus 1 part of the cyclotomic character. Right, so with some fixed representation, VKAP, which is a pretty standard thing. And so you may as well ask what the reduction of this is. So here there's a little technical point here. Let me just make this technical point again for the experts. This is true if AP squared is not equal to 4pk minus 1. It's known to be true. But so you can now forget about everything I said here and just worry about the reductions of these crystalline representations. And then you don't need to impose this condition at all. Okay, so this is known in a few cases. Can I write here? Maybe not. Okay, so the reduction is completely known. So for now, I'm going to assume that the slope is positive. So it's known if in these few cases, so small weights. So when I was a graduate student, this was the range, I think, for which things were known. And this was a very famous theorem of Fontaine and Edix-Oven. And in this case, the reduction looked like, so I won't write, if you don't mind, I'm not going to write the GP squared to GP. I didn't say what this was, by the way. This was the Galois group of the quadratic unramified extension of QP. Right? So there's an induction from here to here. Right? So I won't write this notation all the time. It's always induction from this index 2 subgroup, the unramified quadratic extension of QP. I'll drop that from now on. So notation. And then Breuil made this sort of incredible breakthrough by extending the range of weights. This is for all slopes, all positive slopes. One knows that the reduction is irreducible. So I think he went all the way to 2p plus 1, but still small weights. And he sort of made these tables of various things. The slope is less than between 0 and 1, it behaves like this. When the slope is 1, it behaves like that. Slope is bigger than 1, it behaves like something else. It's sort of already getting very complicated. So this was in about 2003. With 2 papers. On the sort of another way to tackle this problem is to so here the weights are bounded, but you could also try and bound the slopes. So the slope is large. It's also known what the reduction is. So large here means that it's bigger than the floor of k minus 2 over p minus 1. So in this case, there's this nice paper of Berger-Lejoux, which says that again you get something irreducible. Well, it can be reducible if p plus 1 divides k minus 1. This bakes into a direct sum of 2 things, but generically it's irreducible. And finally, it's also known if the slope is small, so in particular in 0, 1, so these answers are fairly clean, except for Breuil's sort of table. These answers are relatively sort of nice. And this is also fairly nice. So this was done by Buzzard and G. So they proved that so need a bit of notation. So there's this sort of, instead of the weight k, this number k minus 2 seems to appear in the subject everywhere. So it's good to have a letter for it. So let's call it R. So the answer depends on the congruence class of R mod p minus 1. And the set of representatives they fix are in this range. So they prove that the reduction is, again, irreducible, a plus 1, except possibly in one very silly case or small case, not silly, but interesting case. When a is 1, and you're in the midpoint of the above range, valuation of AP is a half. When the following thing is also possible. In this reducible case, so I won't tell you what the lambda is. It's a bit complicated, the formula for lambda. But if you restrict to inertia, the mu lambda goes away. You get a direct sum of powers of the mod p cyclotomic character. It's just this sort of scalar thing, omega plus omega. So this happens in a very, very special case when A is 1, one particular congruence class and one particular slope. And yeah, and they actually, there's a subsequent paper of Buzzard and G where they actually say exactly when that happens. It's some complicated inequality involving R, AP, various other things. Okay, so I won't write that down. So that's pretty much all that was known. This was done about 2009, and then their more recent thing was 2013. And they gave a complete, they completely explained this case when it happens. Okay, so it seemed natural to try and push some of these, this particular theorem forward. So let me do this on a bigger board. So in this talk, I want to talk about slopes between 1 and 2, the next range of fractional slopes, strictly between 1 and 2. So this is work completed about 6 months ago. And more recently, we also decided to treat this case of slope 1, which sort of missed the midpoint, integral slope 1. So I'll tell you a little bit about both of them. The first one is joint work with my graduate student Shalini, and the second one is with Shalini and Sandra Rozensztajn at Lyon. Okay, so here is the first theorem. I want to state this, bear with me, this is a little technical, the results, but I want to state it so that you see how complicated things are getting. So far everything's been relatively simple except for this Breuil thing, but it's not so bad. So there are a few cases, so to do this, I need some more notation. Let me just put that up here. So let R, maybe I can do that here. So I'm going to change the set of representatives mod p minus 1. So fix R. So let R be congruent to B instead of A. And let's fix the set of representatives to be in this set. So set of representatives mod p minus 1. And for simplicity, I'm going to assume R is bigger than 2p, and I said p was bigger than 5. Okay, so all this holds for the rest of the talk. Okay, so first theorem. So let's do the fractional slope case first in 1, 2. Let me say up to semi-simplification. So again, the answer depends on congruence classes, but it depends not just on the congruence class mod p minus 1, but it actually depends on the congruence class essentially mod p and mod p minus 1. So mod p squared minus p. So I think the best way to write it would be something like this. The congruence classes at the extremities of this range, 2 and p are slightly, need to be treated differently. And the generic case are the other congruence classes. Okay. So in the congruence classes 2, mod p minus 1, you basically get two various kinds of irreducible things. Notice that this one is very similar to the buzzer G thing. B is basically congruent to A mod p minus 1. But there's this additional possibility that happens in some rare cases, and I better get, yeah, I think that's right, yeah. Okay, so in addition to what happened there, there's this additional thing that can happen. Let's do the generic case. So in this case, these things get flipped in the following sense. This is if p divides r minus b. This is if p does not divide r. Sorry, p does not divide r minus b, and p divides r minus b. So still irreducible. And finally, the last congruence class, which is really tricky. Something sort of surprising happens here. So if p squared does not divide r minus b, you get this irreducible thing. But if p squared does divide r minus b, then you get something reducible, and it's I is the square root of minus 1. Okay, so that's what the reduction looks like in these cases. And there's a mild hypothesis that we work under only when b is equal to 3. So let me write that down. it's similar to sort of something similar to what happens over here, A equals 1 case. So the hypothesis star is that when B is equal to 3, and you're in the midpoint, we assume some sort of p-distinguished kind of thing. So we assume that AP squared so AP squared divided by p cubed is a unit, right? The valuation of AP is 3/2. So this has valuation 3. This has valuation 3. Right? That's just a unit. So this is a non-zero element of FP bar. We assume that this is not equal to this following strange thing. So these two binomial coefficients. It's like some sort of p-distinguished condition. So it's a very specific condition. It's only for one congruence class, B equals 3, midpoint, slope, and some p-distinguished condition. At that point, everywhere else we don't need this condition. Okay, the paper was getting long enough with, it's already 40 pages without this, actually 80 pages. We did weights up to p squared minus 1 in a previous paper, another 40 pages to sort of do this. So, got a bit tired. Sorry? 40 pages, yeah. It may happen that way. So when we did the first thing up to weights p squared minus p, it looked like it was going to be completely chaotic, but somehow it converged into something reasonably simple. So one thing you can take away from this is at least it's generically irreducible. Because the generic case is most congruence classes, most of the time p does not divide r minus b, so this third line here is the generic case, and that's the generic answer. In any other cases, mostly it's irreducible also, except in this very strange case where it turns out to be reducible. Okay, so what about slope 1? This is really recent work. So if the slope is 1, so again, I'm going to sort of impose this kind of theorem on you. I apologize. I'm a little excited about it because it's sort of just been done recently, but maybe when I give these talks later, I won't write all these details down. Let me just write it out completely in the case of slope 1. So let me do the generic case first, maybe. So b equals 2 again is a little strangely behaved. So in this case, you get something reducible generically. Where lambda is this sort of incredible constant. Well, it gets worse than this, but it's already kind of strange. So p does not divide b minus r minus b. So this is well defined. And AP over p is a unit. The slope of AP is 1. So you take its mod p reduction. And otherwise, it is reducible. Sorry, irreducible. So that's a bit strange also. When b equals p, you get this basically scalar thing. And this time, lambda is given by this formula. Okay, so far so good. And finally, this b equals 2 case. I don't think I've left enough space. Move it over here. So this is where this really strange constant comes up. R choose 2 p squared all over PAP. So notice that this number can be 0 because the valuation of the numerator could be bigger than the valuation of the denominator. The slope here, AP is 1, the slope of P is 1, so the slope here is 2. These things both have slope 2, but the difference may have slope bigger than 2, so this number may vanish. And that's not very good. If lambda is 0, these characters are not defined. So this is only when lambda is non-zero. And when the same lambda is 0, then it's something like this. Again, this is same case, P not dividing R minus B. And finally, when P divides R minus B, and this is really the last technical thing in the talk, I think, you get something like induction omega 2 cubed. Okay, so it's not surprising that the boundary 1, slope 1 was, a natural boundary. It's complicated. This is sort of more or less the complete answer. Oh, I should say there's a small hypothesis again, P distinguished hypothesis. And that happens when B is equal to 2. Let me put a star here. So in this last case here, this is if there's some kind of P distinguished thing here. This is if AP over P squared bar is not equal to 1. Okay, so just in that one very special case, we want AP over P bar not to be plus minus 1. Otherwise, okay, so maybe this corollary should have been stated as the theorem. So generically, at least, irreducible if the slopes are fractional in 1, 2, and it's generically reducible if the slope is integral and equal to 1. That's sort of a summary of those two boards. Okay, so that's good, but what's perhaps more interesting is the proof, which uses very beautiful ideas involving the Langlands correspondences. Okay, so let me tell you a little bit about the proof. So in one line, it's always good to give a one-line proof first. So one has this p-adic local Langlands correspondence. Which takes these crystalline representations to these p-adic Banach spaces, unitary Banach spaces. There's a norm on these things, G-invariant norm. And you can reduce on both sides. So this is the thing we're interested in, the reduction of the Galois representation, local Galois representation. But there's also a mod p local Langlands correspondence. And this, so let me call it LL. I can't call both of these LL. They're both Langlands correspondences. One is p-adic, so B for Banach and LL for local Langlands, right? So turns out that this diagram commutes, which is sort of so in other words, if you want to study the reduction on this side, you could try and go to the automorphic side, reduce there, and try and compute the reduction. And if this map was a bijection, unfortunately it's not, then you would just be able to invert this map, right? Go three ways around the square. But this map is injective. So I'll tell you what it is in a second. So let me write it like this. So the mod p local Langlands correspondence is injective. So you just go 3 ways around the square. You do this, compute the reduction, and then you can recognize it because it comes from a unique thing over here. And that's how you get the answer. Okay, so let me tell you, I think there's a seminar about this here. Done the mod p local Langlands correspondence yet? Or maybe I'll say a few words about it. So this is all very classical things. It's just GL2 over QP, where everything's completely well understood now. There's much more progress now for GLN or arbitrary local fields, but okay. Okay, so recall, what is this map LL? So let's fix some notation. So let G be GL to QP. GL to ZP, K. Z be QP star, center. There are these representations, VR, which are going to be representations of GL to FP. So these are representations of GL to FP, and therefore of K. And therefore of KZ, you just make the uniformizer act trivially. The diagonal matrix P00P acts trivially. So more notation. Lambda is always an FP bar. Let's fix a character eta from, so this is a smooth character, smooth mod P character. Sorry, I have to come over here. Okay, so in terms of that data, there's this basic representation, which is usually denoted by pi r lambda eta, and it's basically it is compact induction. Then you take the co-kernel of the Heck operator T minus lambda. I'll explain that in a second, and then you tensor with eta. So we have all the data r, lambda, and eta. So this is only for r small. So when r is small, it turns out that this representation, so this is just the induced representation from usual symmetric power representation, induce it up to G. So compactly supported functions, mod the center, functions from G to VR. It turns out that the G-linear maps of this space, so it's generated by one, it's not irreducible. Schur's lemma is now known to hold there. So there's this one Heck operator, which is a non-scalar endomorphism. That's the Heck operator T. And if you take the co-kernel with T, you generically get something irreducible, or with T minus lambda. So this is just, when I saw this notation first, it looks really confusing, but it's actually T minus lambda applied to this induction. Right? But nobody writes that. It's too much stuff. It just means co-kernel. And then you tensor with this character. So these are generically irreducible. So for some small values of r, like r equals 0 and p minus 1 and things like that, and some special values of lambda, this thing becomes reducible. But it's generically irreducible. And then in terms of these representations, here's the mod P local Langlands correspondence. So on the Galois side, let me get some more space here. So these irreducible Galois representations, fundamental characters of level 2, they correspond to these so-called supersingular representations when lambda is 0. And when you have something reducible on the Galois side, so fundamental characters of level 1 basically showing up. In this case, you get something a little strange when you first see it, but get used to it. So it's actually a direct sum of two generically irreducible representations, so two principal series. Remember, lambda is not 0, so this is, oh, sorry, I should have said here lambda when lambda is not 0. Direct sum p minus 3 minus r, lambda inverse eta omega r plus 1. So there's a square bracket here to denote that you should be in the right range. So these are things in p, this is congruent to p minus 3 minus r mod p minus 1. And this square bracket thing lies between 0 and p minus 2. Okay, so just in words, irreducibles correspond to supersingulars or supercuspidals. Reducibles, as one should expect, correspond to principal series, but actually direct sum of two principal series here. This turns out to be a principal. Doesn't look like it at all because we're doing compact induction from K, but these can be written in induction from the Breuil as well. So these are some sort of principal series representations. And you take a direct sum of them, and so you can already see why this thing is not going to be surjective, right? It's hard to hit one particular principal series. You hit these sort of sums of principal series. But by definition, it is injective. Okay, so that was just a recall of this bottom line here. It's a very explicit map, and it tells you what to do with any particular Galois representation, what to map it to. Okay, so now we need to go around this square. Let me tell you how that's done. So by what I've said so far, it's enough to compute the reduction of this Banach thing by the injectivity of this bottom map. Okay, so here's the way to do that. And these are all fairly standard things. So a few more technical things, and I'll start getting to how one does things in the particular ranges of slopes we're interested in. So let pi k ap be some sort of characteristic zero analog of this compact induction thing. Again, there's a Heck operator, which is G linear. You go take the co-kernel, T minus AP. Let's define the following lattice inside capital pi k. So this is a G module. These are just functions from G to this space, characteristic zero space, with the G action on the right. So there's this lattice. You can just look at the integral things, integral functions. Okay, so and finally, you can reduce this lattice mod P . So let's define theta bar to be the mod P reduction of this thing, of theta, capital theta. Okay, so it's a fact that this thing is actually also isomorphic to the reduction of the Banach space, and by the community of that square. Okay, so this is a key point. It sort of makes everything much more computable. So everything is fairly relatively abstract now, but now we have something very concrete, this particular representation and its reduction, and it agrees with all other things in this lower right corner here. Yeah, everywhere there's semi-simplification. Yeah, sorry, I should keep saying that everywhere. This is the semi-simple local Langlands correspondence. There are non-semi-simple versions, but they're much more sort of difficult to state. And I didn't tell you that sort of in some of these examples, you can ask whether the reduction is per MFE or third MFE. You have sort of a shoulder, and you can sort of use the non-semi-simple mod p local Langlands correspondences to discuss those things, but that's a bit more technical. So yeah, everything is semi-simple here. Okay, so we have this theta k AP. So how does one? So it's enough to compute. All right. So I'll go back here for a second and write the following thing. So by one of the isomorphism theorems one learns in undergraduate algebra, this is just induction kzg sim r zp bar squared modulo t minus ap induction kzg sim r qp bar squared intersection with the integral things. Right? I mean, this is just the domain of that map, and this is the kernel. You're looking at all things in here which line the denominator here. So after you apply t minus ap, there's still integral. This is perhaps the most important line of the talk, this sort of weird denominator here. It is not, so this thing is not the more naive thing that you might think it might be, sim r zp bar squared modulo t minus ap induction kz to g sim r zp bar squared. It's not that. It's actually this slightly more subtle thing, but it's fairly obvious from the definition. And so to compute theta bar, one uses this description of theta quite often. You sort of work with functions such that after you apply t, they're sort of functions with some mild denominators. After you apply the Heck operator to them, you want them to become integral. Okay, so those are the functions that are going to be in theta, and reducing mod p, they're going to be in theta bar. Okay, so it's enough to compute theta bar. Any questions before I move on? Okay, so let's do that. So the first remark is, so theta bar is a mod p thing. So there's clearly a map from here to theta bar. VR, remember, was the space of, so it's sim r fp bar, so mod p thing, symmetric powers mod p. Right? It's coming from, there's a map from int r zp bar square, the integral thing, to theta bar. And then since the theta bar is mod p, it factors through mod p thing on the left. Okay, now this is a finite length representation. This is unfortunately a huge thing. As you well know, the symmetric powers mod p are only irreducible for some small range, right, from 0 to p minus 1. And after that, this thing becomes very complicated, though it can be completely described. And when you induce it, you get all kinds of things. So this is a huge representation, and this is finite length. So one is trying to compute this by somehow getting a handle of the kernel of this map. Okay, so here's a very nice observation of Buzzard and G. So they do it much more generally, but let me just say it in this special case. So they remark that when your evaluation is in a particular range, you can actually write down what this kernel is to some extent. Not completely, but to some extent. So in particular, so let me write VR, since we're starting to do some computations now. as the set, sort of the homogeneous polynomials of degree r in two variables, x and y, over fp bar. Okay, so that's the usual module for the symmetric power representation, and then GL2FP acts in the usual way on the variables x and y by x goes to ax plus cy and y goes to bx plus dy, something like that. And therefore, it's a kz module, etc. Right? K just subjects to GL2FP. Z acts trivially. I mean, the uniformizer and Z acts trivially. Okay, so it turns out that if the valuation is bigger than 1, then you know that the following space, so this is going to be the submodule of VR generated by the second highest monomial. Okay, so this turns out to be in the kernel of the map above. And if the valuation of AP, so this is a sketch of now theorem A. So far everything was completely general, but now I'm specializing to slopes between 1 and 2. If your slope is less than 2, then you know another submodule is in the kernel. And I don't have space here, so let me write it here. So VR double star is all polynomials divisible by twice divisible by theta. So theta squared divides p, and theta, where can I write that? Over here. Theta is this very special polynomial, Ramanujan's polynomial, xpy minus xyp. So we're looking at all polynomials, mod p polynomials, which are twice divisible by theta. Okay, so that's the starting point of the computation. Okay, so because of this map here, maybe I should have given it a name. I don't know, phi or something. Kernel of phi. Kernel of phi. So therefore, phi factors via the following quotient Q, where Q is the induction functor is exact, so you can bring these things inside the induction. This quotient. Okay, so this has already made the problem a lot more controllable. VR is some huge space of polynomials of degree r. And r, as the weight grows, as k grows, r minus 2 also grows. This becomes very big. But this sort of compensates because the codimension here of VR double star is 2p plus 2. So the dimension here is not so big. It's just 2p plus 2. And then you're further modding out by some more polynomials. And so you're controlling. This is quite well controlled, the dimension of this. But still, it may have many Jordan-Holder factors. Okay, so the question is to study Q now. We call Q for sort of the final quotient in our paper, because that's where sort of the computations start. So here is a proposition. Let me call it proposition X for xr minus 1. Maybe it should be xr minus 1. So the length of xr minus 1 is either 2, 3, or 4. So this is one fact. So it's not irreducible. If it was irreducible, you'd be in pretty good shape, because what would happen is that theta bar has finite length. If this was just one Jordan-Holder factor, then you could just sort of use the local Langlands correspondence to more or less guess what the kernel of that should be. Okay, but this has up to 4 Jordan-Holder factors. And you can actually say which weights appear in Q, completely describe it, in terms of some very strange p-adic expansions of r minus 1, some of the p-adic digits of r minus 1. So I won't write the technical theorem down, but you can do that. But maybe I'll write the following corollary down. So you can describe the Jordan-Holder factors. So we don't need this in the talk, but let me just say it. It's a nice little formula. So So the dimension of xr minus 1 is p plus 1 minus sigma. This is if sigma is less than or equal to p minus 1, and it's 2p plus 2 if sigma is strictly bigger than p minus 1, where so write r as p to the n times u. So sigma is the sum of the p-adic digits in the base p expansion of u minus 1. And delta is just 0 or 1 depending on whether p divides r or not. Okay, so the first sort of order of business is to somehow completely control this module xr minus 1. It's incredible that there's nothing, we couldn't find anything in the literature about submodules of symmetric power polynomials. This is sort of high school mathematics. You have the top monomial x to the r, you're looking at the G module generated by it, and you try to write down a structure completely. That's pretty well known. So there's some work of Glover, I'm sure how to pronounce his name, which tells you how to do it for the top monomial. But for some sort of second highest monomial or third highest monomial, look at the G module, GL2FP module generated by it. Seems to be not much information about it. So this deals with that. So once you have an idea of what xr minus 1 is, proposition x, you know what the denominator looks like a little better of q, and therefore you know what q looks like. And it turns out that q, because of this, has, it can be irreducible, sorry, I was wrong there. So it has 1, 2, or 3 Jordan-Holder factors. This is all as a KZ module or as a GL2FP module. Or as a K module, or as a KZ module. Z basically acting trivially. Okay, so when you're in this case, you can conclude immediately. And this is what happens in the Buzzard G range. They basically mod out by the highest monomial here, and all polynomials which are once divisible by theta, and they show that this thing is irreducible. That pretty much finishes the argument, because then you just stare at the mod p local Langlands correspondence and can conclude what theta bar is. But unfortunately, this happens very rarely when the slope is between 1 and 2. So we can conclude here immediately. This is the generic case. And we're really surprised to see examples where this happens too. So those are the most tricky cases, and that's where that hypothesis star comes from. Okay, so what do you do when you have 2 or 3 Jordan-Holder factors here? Well, the one thing we haven't used is, did I erase it? I think I just erased it. You have to sort of kill some of these Jordan-Holder factors. So use T, so I'll just be a little vague here, to kill superfluous Jordan-Holder factors, and conclude by the mod p local Langlands correspondence. So actually, most of the work is in this last line, because it's not at all clear which Jordan-Holder factor you have to kill. There's no one to tell you which one to kill. And even killing any particular one, you always wind up with, start with any function, you always wind up with 0 most of the time. So when you're trying to kill something, you want to get something non-zero. So let me try and explain that in one example, to give a flavor of what this last line means. I mean, you have to do this for all weights. So let me just fix one very special weight and do it in the last 5 minutes give you some feeling of what this means. So here's an example. So let's fix the weight r to be 2p plus 1. So remember, Breuil had already done things up to weights 2p plus 1. That's r less than 2p minus 1. So the next weight is really r equals 2p. But let's skip that one and do the the next one. There's some interesting phenomena there. So in the notation of the theorem, this is congruent to 3 mod p minus 1. Right? So b is 3. B were these mod p representatives, mod p minus 1 representatives. OK, so here's a function. I'm going to write down just randomly. These are the things that you have to sort of come up with. I'm going to use some strange notation here. I'll explain in a second. OK, so f2 is a function from g to sim r qp bar squared. It's a characteristic 0 function. R is, notice the degree of this polynomial is 2p plus 1, homogeneous, but it has some denominators in it. The square bracket notation is just some standard notation for functions. These are basically some sort of characteristic functions. So gv, for g belonging to g and v belonging to vector space v, is a function from g to v which takes g prime to g prime dot g prime gv. G prime belongs to kzg inverse and 0 otherwise. Okay, so there are these basic functions g square bracket, and this notation here are just some sort of matrices. So the notation g m lambda 0 just means this matrix. So this is an element of G. OK, so you have this slightly rational function. It's rational because it has just a denominator p. You apply t minus ap to this function, f2, and compute for a while. And it turns out that when you, so it turns out that I was trying to do an example, so I should have said this before. In this case, it turns out that Q has 2 Jordan-Holder factors, J1 and J2. It's a generic, sort of generic case. And they are V P minus B, this B, plus 1 tensor DB minus 1. And this one is VP minus B minus 1 tensor DB. D is determinant. Ah, yeah. So lambda was an element of FP, but these lambdas are in ZP. So those are Teichmuller lifts. This is GL2 QP, so it has to be something characteristic 0. So square bracket lambda is. So you do this computation, and you come up with the following. This is just one weight. So everything's very fixed. P is bigger than 5, so 2 and 3 make sense. You can invert 3, etc. You come up with this characteristic function when you project to J2. So you do this in characteristic 0. When you apply t minus ap, first of all, you get something integral. So you get something in the denominator of that theta thing that I was talking about. And then you go mod p so that you're in Q. And now the question is, when you project to J1 or J2, do you get something interesting? When you project to J2, you actually get something non-zero. OK, well, that's good, because such functions are 0 in theta, right? In particular, and this is a very simple kind of function. It's just g comma a vector. So that shows that J2 actually dies. So this function actually generates induction J2. Because if you make g act on the left, you can basically get everything here. So using this particular function, you can actually kill J2. And you can show that this thing factors through just J1. And now I chose this example because You're almost done, but not quite. So now, remember we had something from int q to theta bar kap. This actually now, we've just shown that it factors through induction J1. Now there's this subtlety whether it actually further factors through induction kz g J1 mod t, or possibly through something quadratic, so this principal series thing. So lots of arrows. So there's one triangle here. The question is which of these triangles occur. Is it the left triangle or the right triangle? Does it further factor through t, or does it further factor through a quadratic thing? This is by the Chinese-Riemann theorem. It breaks into two factors. This is like the sum of two principal series, right? And this thing is basically the supersingular things. Okay, and then once you know which one of these occurs, you get theta bar immediately. This would be, for example, this is irreducible, right? These are supersingular. This is exactly pi r 0 eta for some r n eta. Yeah, you can work out what these r and etas are here. So this is irreducible. So you immediately get that theta bar is this supersingular thing, and you could determine it. In this case, you get a direct sum of two principals. You have to, OK, so again, you have to come up with some new functions. I won't write them down this time. But you can come up with some new functions, f2. I'm calling them f2 because these are functions on the building, and they're sort of length 2 from the origin. The reason one has to go to length 2 is that as the weights go higher, there are many correction terms going down, length 1, length 0, etc. So I'm not writing those here. This is a very simple example. Anyway, it turns out that this example occurred. This is what's actually happens. I could write a few more lines, but maybe you don't want to hear that. And yeah, so therefore, you get that by the mod p local Langlands correspondence, you get induction of omega 2 to the p plus 3. Number 3 was b. So it's just one particular weight. So if you go back to your notes and look at the first page, that's the sort of answer you get. OK, so I'll stop there.